So here we have the abstract class abstract graph that we were talking about before. Now if we want a concrete version of it, all we've got to do is we've got to define these three methods: neighbours, weight, which we'll come to later, and vertices. So we can have different implementations of abstract graphs, and then all these, the path methods, the shortest path methods will still work because they're defined in terms of these things. So provided we give concrete versions of these things, then we'll be able to use our shortest path. So here is a concretization, if you like, of abstract graphs. So I've got something called array graph. And the reason it's called array graph is because we're representing a graph as an adjacency matrix. So we have this two-dimensional array of doubles. Why did I have doubles there? Oh yes, well, I'll come to that later. But later we'll see that we're talking about weighted graphs, but this is simpler. So the neighbours. So in this adjacency matrix, if the value is greater than 0, then it means there's a connection between the two nodes in the graph. So to find all the neighbours of a thing, of a node, we just check whether in the adjacency matrix column corresponding to the vertex we're interested in, if that component is greater than 0, it means that there's an edge connecting V to J. So we add it to our set K. So here we loop through each edge, and if in the adjacency matrix the weight of Vj is greater than 0, it means that there is a connection. So we add it to the set. So here we've got our neighbours, and this is where we work out all the vertices of our graph. So basically, there'll be a vertex corresponding to each element of the adjacency matrix. So again, we're assuming that the nodes start at 0. So it's simply the length of the one more than the length of the the length of the adjacency matrix will tell us what the vertices are. So the vertices go 0, 1, 2, 3, 4, etc. So how do we? So that's a particular implementation of our graphs. So the next thing I want to show you is some useful stuff for manipulating, for getting those stuff from those files and creating graphs. So we have the stations, the roots, and the edges. So the edges.txt is the thing that tells us which station is connected to what. So remember, the stations had values, IDs going from 0 up to whatever the last station was. So let's see what we do here. So right, what we do is we have we're going to use a map. I've used a tree map. We've done maps before. So every station ID gives us a corresponding string, which is the name of the station. So if I have an array list of integers, I can convert that to representing a path, say in a route on an underground map. They're represented as integers, but if I want to convert them to strings, what I have to do is get the name corresponding to each station ID. So I have to get the name corresponding to each thing. and I do that for each integer in my array list. So similarly, I can convert a set of paths which are made up of integers into a set of paths that are made up of strings. So that's useful for printing out these things, because it's more useful if I print out the names of the stations, like Baker Street, Marylebone Road, rather than the actual numbers, which won't mean much to anyone. So here's my here's my edges ij is my adjacency matrix. So I set everything to 0, and then I read my file edges.txt, and I split it between a comma. Now, if there's a 1 in there, it means that if there's a 1 there in that position, it means that there's a connection. So then I add I put a 1 in that place in my adjacency matrix in both, because it's symmetrical, because there's a path from 0 to 1 and also a path from 1 to 0. So I fill up my my adjacency matrix. Here I'm filling up my map. So now the map will map the numbers to the map will now map the numbers to the strings corresponding to the stations. So I've got everything I need. So what I'm going to do is I'm going to have to create a graph using this. I'm going to have to create a graph using this, what's this here? This is the constructor, where I pass it the edges adjacency matrix that I defined here, and then I can simply use the shortest paths method in one step. So this shouldn't be very difficult for you, but just to show you how to do it, so here's the code that you've already seen with the edges and the stations. Now the extra thing you have to do is you create the array graph using its constructor using this adjacency matrix. Then we read in 2 values for the station names, for the station IDs, and then we work out, we call G and the shortest paths in first and second, so that'll find the shortest paths in our graph, and then we convert that to a list of names rather than a list of numbers, or a set of lists of names rather than a list of numbers. So basically all you've got to do is add this stuff to the station handling code that I showed you here. So at the bottom here we've just got a few more. We just need a little bit more here. There's another slight difference I've noticed. In this one here I call them edges.txt, and in this one here I call them edges. So you have to be careful that your file name, you've got the file names right in the directory that you're working on. So that should be enough of a hint for you to do the first coursework question.